All right, here we get to have the opportunity to watch and learn a little bit about relativity. And we'll be talking about both special and general relativity and how Albert Einstein kind of came to these conclusions that have revolutionized the world of physics. So it all begins with light, and light is born in the nuclear furnaces within the core of stars. So here's a cross-section profile of an average star, right? Our sun. In the inner core, this is where the nuclear fusion takes place, where we're taking hydrogen and we're compressing it, high pressure, high temperature, and it is creating heavier elements in the form of helium and so on, and other heavier elements. And then the photon, this secondary product of creating helium, is light in the form of photons, and they gradually eke their way to the surface where they are given out of the photosphere and they are blasted off into space in the form of the photon that we've talked about with the electromagnetic spectrum. So here's a picture from class that a star that's forming forms out of this solar nebular region that's primarily hydrogen and helium gas, and this is compressing high temperature, high pressure. This is taking place in the cores of all stars, and this is where we find nuclear fusion taking place. So we're going to be looking at how E equals mc squared, right? Energy is equal to mass times the speed of light squared. That energy and matter are really kind of the same thing. So within a star, we have this thermonuclear fusion. And what we could say here is that if I put 4 hydrogen atoms together, this process is called a proton-proton chain, we create helium along with a secondary product of energy that's released. So since E equals mc squared, matter is converted into energy that we see as sunlight. But we can do some simple math here, and we can see that 4 hydrogens fused into helium through this process, that if I do the math, if I take 1.008, which is the atomic mass of hydrogen, and I multiply that times 4, the numbers don't add up. It doesn't add up to the atomic mass of helium. And this is because, so if I take 4 times 1.008, I get 4.032, but helium's atomic mass is 4.003. It doesn't equal 4.032. The missing mass is actually the conversion into pure energy and light. So that light that we're referring to is located on the electromagnetic spectrum. Now here's my gamma, my X-rays, my UV. These are the high frequency, high energy, short wavelength, right, even into visible light. And then I have my infrared, IR, microwave, and radio waves, which are my larger wavelength or long wave parts of the electromagnetic spectrum here. The speed of light is the speed limit of the universe. And every part of the electromagnetic spectrum, everything up here, is pure energy traveling at the speed of light. But because the speed of light is what it is and does what it does, there are some interesting consequences. Nothing can travel faster than it. This is the cosmic speed limit. Even gravity abides by the speed of light. Matter and energy are really the same thing. They're just organized a little differently. E equals mc squared. Energy and matter are not only related, they're kind of one and the same. And it only takes a tiny amount of matter to be converted into tremendous amounts of energy. Right? When I multiply something times 186,282 miles per second and I square that value, it gets pretty big pretty quick. And the sun is continually providing the Earth with energy, combining hydrogen into helium through thermonuclear fusion. And this is where we can see the direct conversion of matter into energy. So here's where things begin to take off. We're going to need to make sure as learning relativity, we have to focus on what's called a frame of reference. So we're going to have an opportunity here to view a video on simultaneity. And I'm going to make sure that you understand that from different reference frames, there can never be agreement on the simultaneity of events. Meaning an observer outside the frame of reference compared to a person in the frame of reference will both experience and view something different. However, both are correct. Here goes.
Imagine 2 observers, one seated in the center of a speeding train car, and another standing on the platform as the train races by. As the center of the car passes the observer on the platform, he sees 2 bolts of lightning strike the car, one on the front and one on the rear. The flashes of light from each strike reach him at the same time, so he concludes that the bolts were simultaneous, since he knows that the light from both strikes traveled the same distance to his eyes at the same speed, the speed of light. He also predicts that his friend on the train will notice the front strike before the rear strike, because from his perspective on the platform, the train is moving to meet the flash at the front and moving away from the flash at the rear. But what does the passenger see? As her friend on the platform predicted, the passenger does notice the flash from the front before the flash from the rear. But her conclusion is very different. As Einstein showed, the speed of the flashes as measured in the reference frame of the train must also be the speed of light. So, because each light pulse travels the same distance from each end of the train to the passenger, she can only conclude one thing. If she sees the front strike first, it actually happened first. Whose interpretation is correct? The observer on the platform, who claims that the strikes happened simultaneously, or the observer on the train, who claims that the front strike happened before the rear strike? Einstein tells us that both are correct, within their own frame of reference. This is a fundamental result of special relativity. From different reference frames, there can never be agreement on the simultaneity of events.
So we can look at that in a similar way if we have somebody standing on a cart with wheels. So if this person, this girl here, throws an object at 10 meters per second to the left, she and everybody observing this object, the object is moving at 10 meters per second. However, if the cart with wheels is moving at 10 meters per second, then an outside observer is going to view the ball moving at 20 meters per second, right? Because her frame of reference is in motion. So the observer views the ball moving at 20 meters per second, while her frame of reference, she's within the frame of reference, she still views it as only traveling at 10 meters per second. And the idea of simultaneity says they're in two different frames of reference, so they cannot have agreement on what is taking place with the ball. So the idea here of relativistic physics from Einstein says that the speed of light makes the rules. It doesn't violate anything. It's simply saying that the flashlight, if we take the same idea, instead of her throwing a ball, she's now turning on a flashlight. These flashlight, the photons, from her perspective, are traveling at the speed of light, right? 3 times 10 to the 8th meter per second. Even if she's moving toward the outside observer, it's still traveling at the speed of light. It's not traveling at the speed of light plus the velocity of the cart. It's traveling at the speed of light. That the speed of light makes the rules in this case here. It doesn't matter if you're within or outside of the frame of reference. The speed of light is the speed of light. So here we can look at how gravity obeys this very rule too. Gravity is not instantaneous. It follows the speed of light. So if the sun were to burn out, so we'll go on this little cosmological this scenario where the sun kind of vaporizes, that the gravitational field would not, of the Earth and the sun would not move or change instantaneously. That the Earth would continue traveling in a straight line, but not until after the light and gravity traveled to us at the same time. So here goes.
To understand this conflict, we have to run a few experiments. And to begin with, let's create a cosmic catastrophe. Imagine that all of a sudden, and without any warning, the sun vaporizes and completely disappears. Now, let's replay that catastrophe and see what effect it would have on the planets according to Newton. Newton's theory predicts that with the destruction of the sun, the planets would immediately fly out of their orbits, careening off into space. In other words, Newton thought that gravity was a force that acts instantaneously across any distance, and so we would immediately feel the effect of the sun's destruction. But Einstein saw a big problem with Newton's theory. A problem that arose from his work with light. Einstein knew light doesn't travel instantaneously. In fact, it takes 8 minutes for the sun's rays to travel the 93 million miles to the Earth. And since he had shown that nothing, not even gravity, can travel faster than light, how could the Earth be released from orbit before the darkness resulting from the sun's disappearance reached our eyes. He found the answer in a new kind of unification.
Einstein came to think of the three dimensions of space and the single dimension of time as bound together in a single fabric of space-time. It was his hope that by understanding the geometry of this four-dimensional fabric of space-time, that he could simply talk about things moving along surfaces in this space-time fabric.
Like the surface of a trampoline, this unified fabric is warped and stretched by heavy objects like planets and stars. And it's this warping or curving of space-time that creates what we feel as gravity. A planet like the Earth is kept in orbit not because the sun reaches out and instantaneously grabs hold of it, as in Newton's theory, but simply because it follows curves in the spatial fabric caused by the sun's presence. So, with this new understanding of gravity, let's rerun the cosmic catastrophe. Let's see what happens now if the sun disappears. The gravitational disturbance that results will form a wave that travels across the spatial fabric in much the same way that a pebble dropped into a pond makes ripples that travel across the surface of the water. So we wouldn't feel a change in our orbit around the sun until this wave reached the Earth. What's more, Einstein calculated that these ripples of gravity travel at exactly the speed of light.
So as a result of the speed of light being this absolute, something has to give. So we're going to start looking at time changing as a result of this.
Imagine the great scientist in a rocket ship, floating in deep space. The ship has powerful headlights, and when Albert switches them on, the light races away from him at, of course, the speed of light, 670 million miles an hour. Now imagine that Albert has a twin brother, Bertrand, who also has a spaceship. Let's say Bertrand flies away from Albert at half the speed of light. When Albert turns on his headlights, how fast would they seem to be going when they overtake Bertrand? You'd think he would see them pass by relatively slowly, like a faster car passing you on the highway. But that's not the way light works. Instead, Bertrand would see Albert's high beams pass him at the full speed of light. Bertrand's own speed makes absolutely no difference.
This prediction of Einstein that the speed of light is the same for everyone is one of the strangest in physics. But it's true. It's been shown by hundreds of experiments. The speed of light is going to be the same, no matter how fast you're moving towards it or away from it.
Even if Bertrand turns around and travels head-on towards Albert, he would still see Albert's headlights pass him at the same speed. So what's going on? Welcome to the realm of time travel. If both brothers see light moving at the same speed, then something else must be changing. That something is time.
Or space and time. It turns out that if an object is moving fast enough through space, it can alter its passage through time.
If Bertrand's ship had some suitable equipment, we could see this mysterious effect for ourselves. This device is a light clock, two mirrors that face each other with a particle of light, or photon, bouncing between them. Each bounce is one tick of the clock, and in the right hands, such a clock shows directly how speed changes time.
These ticks would normally occur millions of times per second, but we have slowed it down to show how this clock works and how the motion of it will affect the rate of ticking. You'll notice that the clock is ticking more slowly as I move it. Why is that? Well, the photon is making a zigzag path